Alright, in the previous video we have discussed the magnetic fields around a straight current carrying conductor, and in this video we are going to start with a magnetic field around a current carrying loop. So in the current carrying loop, we are performing the experiment same as we have performed with the straight current carrying conductor. Now what it is? We are having a cardboard. In this cardboard, we have made two holes through which the loop is going to pass. This is a wire which is in the shape of this loop, and it is going to be attached with a battery, a rheostat, ammeter, and a key or a switch. So this is the circuit diagram, and again some iron fillings, they are being scattered all over this board. When no current is drawn, which means the circuit is open, the switch is open, and I am tapping the cardboard once, I am tapping the cardboard again, nothing, no observation is going to be there. The iron fillings, they are still scattered. On closing the circuit, and the current is now going to pass through this loop in this direction, which is the clockwise direction. In the clockwise direction, the current will flow in this loop. So current is in the clockwise direction, as we know. The current is in the clockwise direction. So this is the clockwise direction of the current. Now, we'll have to see the magnetic fields around it. Till now, we have the understanding of only one rule, which is the right hand thumb rule. So we'll imagine that this portion is the straight portion where it is entering in, or when it is moving out from this. It is entering in from one and it is moving out from the cardboard on the other side. So at this point we are assuming that it is the straight current carrying conductor. Now we'll see. When the current is moving upward, the rule says the thumb will point in the direction of the current. So thumb is pointing in the direction of current, which is upward, and the magnetic fields, it is going to be curl in the anti-clockwise direction. The magnetic fields, they are going to curl in the anti-clockwise direction. So we know they are closed circular loops at the center. They are very concentrated. They are very concentrated at the center. And the direction is anti-clockwise. The direction is anti-clockwise. So we have made this direction. On the other side, the current is moving downwards. The magnetic field lines, they are going to set up in the clockwise direction. Current is downward, so thumb is downward. And the magnetic fields, they are in the clockwise direction. The magnetic fields, they are in the clockwise direction. Again, the closed circular loops, they are forming. They are forming the closed circular loops. So this is how the clockwise direction of the magnetic field is. Here it is anti-clockwise because of the rule. Here it is clockwise again because of the right hand thumb rule. But the thing which is to observe is at the center of this cardboard. At the center of this cardboard, we are seeing that magnetic field lines, they are appearing to be straight. They are not that curled, but they are straight. Why this has happened? Now, as we are moving away from the conductor, the strength of the magnetic field, it is going to decrease. If the strength is going to decrease, the loops, they tend to increase their radius because they are now no more concentrated because of the lack of magnetic field. If they are expanding, then they are forming a great radius. The radius is very, very high, very, very large radius. And as the radius increases, the point of our observation, it gets straightened up. This appears to be straight, but it is curled. But why we are observing it to be almost straight? Because radius is very, very high and the portion which we are observing is very small, so it seems to be a straight line. Similarly, over this, when we are moving away from this conductor, they are also of the great radius. They are also of the great radius. So that is why at center, we are seeing these parallel lines. We are seeing these parallel lines. And the thing that we know is if the magnetic field lines, they are parallel and distance between them is same. So we can say these are parallel and equidistant. The magnetic field lines, they are parallel as well as equidistant. Then we can say that these magnetic field lines are uniform magnetic field lines if the distance is same and they are parallel. In this case, the distance is almost same and they appears to be parallel. So we can say that these are the uniform magnetic field. These at the center of this cardboard, they are forming the uniform magnetic field lines, and near to these current carrying conductor, they are forming the closed circular loops. Now the next very important thing is this current carrying loop acts as a dipole, which means it is forming two poles. One is the north pole, other is the south pole, similarly to that of a bar magnet. But for that we'll have to first see how the bar magnet is acting. We know outside the magnet, the magnetic field lines, they flow from north pole and they ends at the south pole, which means they are emerging from north and entering into the south pole. Again, they are starting from the north pole and getting into the south pole. So moving out, and then entering into the south pole, moving out and entering into the south pole. Means the exit of this magnetic field lines is always from the north pole and entry is always from the south pole. So north pole will be pushing the magnetic field lines to move out. South pole will grasp the magnetic field lines into it. Now let us see what is happening. When in this conductor, you will have to see, let me make a central axis so that you can have a great understanding. So this is the central axis. This is the central axis. Alright. This wire, let me name this wire as, this is the starting point as A, this is C. So if this AC, this is the AC and this is the left hand side of AC and this is the right hand side of AC. The left hand side of AC is this, the right hand side of AC is this. Now, if the current is moving upward, we know that in this the current is moving upward. So current is moving upward, magnetic field lines, they are going to move out. They are going to move out. This is moving out on the left hand side of this wire. Just imagine that I am holding the wire in my hand and on the left hand, this is the wire that I am holding. On the left hand side of the wire, these magnetic field lines, they are moving out. If they are moving out, magnetic field lines, they are moving out. Moving out is the property of the north pole. It is the property of the north pole. So on the left hand side, the magnetic field lines are moving out. So this is the property of the north pole. So on the left hand side, we are having the north pole. What is happening on the right hand side then? Now, when we are considering the right hand side, this is the wire. On the right hand side, this is the wire on the right hand side, they are going to move in. On the right hand side of the wire, they are going to move in. Getting in, grasping in is the property of the south pole. So let me write down, on the right hand side, it is the south pole. On the left hand side, it is moving out. On the right hand side, it is moving in. So moving out is the property of the north pole and getting in is the property of the south pole. Alright, let us see how this criteria is following on this side. Let me consider this as CB. This wire is now CB. This is the left hand side of CB and this is the right hand side of CB. Now, again, I am holding the wire in my hand. Current is moving downwards. In this case, now, at this side, on the right hand side of the wire, this is the wire, on the right hand side of the wire, the magnetic field lines, they are moving out. Magnetic field lines, they are moving out. Moving out, on the right hand side, they are moving out. This is the wire and they are moving out. Moving out is the property of the north pole again. So here, the polarity outside is the north pole. And on the left hand side of this CB is they are moving in. Moving in is the property of the south pole. So inside we are having the South Pole. Outside we are having the South Pole. Inside this in both cases we are having the South Pole. This portion of loop, this entire portion of loop is known as the face of loop. This entire portion is known as the face of loop, and the face of loop is forming in both cases the South Pole. When it is forming the South Pole, when current is flowing in the clockwise direction. When the current is flowing in the clockwise direction in this loop, current is flowing in the clockwise direction. Now, the thing that we inferred from here is, outside the loop it is North Pole, inside is South, and outside is North, which means we can conclude that at the face of the loop it always forms the South Pole when current is clockwise, and outside the loop it always forms North Pole when the current is in the clockwise direction. So at the face of loop it is South Pole, outside it is North Pole. So it has forms two poles, one is the South Pole which is inside and North Pole which is outside. So we can clearly say that current carrying loop act as a dipole. Dipole means two poles. As magnet is having two poles, this is also having two poles, in which magnetic field lines, they are moving out from outside and moving in inside, moving out from outside and moving in inside when the current is flowing in the clockwise direction. So this was all about the magnetic field lines along a current carrying loop. In the following video, we'll discuss one most important rule, which is the clock rule, their explanation, and then we'll see it is formed out from the right hand thumb rule. So we can also say it is an extension of the right hand thumb rule. So in the next video, we'll discuss the next rule as clock rule.